Okay, hello guys. So I'm recording this video because I felt like maybe many of you who are used to using the sequential API and the simple method of implementing CNNs or ANDs with TensorFlow would like to sort of see how it translates into a more versatile functional API, basically. So I'm going to run a very simple project in parallel, one with sequential and one with functional API and a gradient tape. Okay. So what we are going to play with is going to be the CFAR database. It's like 10 classes of images basically. So we're going to be doing a CNN classification. Uh, I'm not going to be talking about CFAR so much, so you need to read about it yourself if you want to know what it is. So I'm going to just be focusing on comparing implementing CNNs via sequential and a functional API with gradient tape. Okay, so first I'm going to go through the sequential model. So from keras.datasets import CFAR, and we're going to make our xtrain, ytrain, xtest, ytest. We're going to take it from basically CFAR 10.load data. So now we have the data. So if I look at the shape in our training data, we have 50,000 images. They are 32 by 32 and their color. Okay. So just to visualize this image, we are going to just take a look. So obviously these are low resolution images. Okay. This is mainly used, for training and all that. So that's what we are dealing with. Okay. Let me just actually get rid of this output perhaps, or because I just don't like it to be clear output. Okay. And obviously extrain max, these are images, so we're going to be having 255 as the maximum value of each pixel, and 0 is going to be, the minimum value for pixel. As usual, we need to do a scaling, and you're all aware that we just use, when you're dealing with images, dividing each of these arrays basically by 255 would basically give you would normalize basically your images, so if I just click on X max, it's 1, and obviously X train is going to be 0. Okay. Now with sequential, there is one thing to pay attention to. So our Y train at the moment is in form of 699. It's coded like that. So for example, I don't know, for a cat it's a 6, for a dog it's a 9, for a car is a 1. Okay. And what we want to do is to code this into categorical column. Okay, so from TensorFlow.keras.utils, import to categorical. So now that we have to categorical, we're going to say ycat train and ycat test to categorical, and we're going to give our array and the number of categories basically. So when we do that, if I just look at, so before our Y train, was like this, whereas let's just do it like this, yeah. So it would have been a number, like number 6. Now, if I say ycat train 0, 1, 2, 3, 4, 5, 6. So it's now coded into a categorical mode, yeah. So instead of one column, it's like these 10 columns basically, and each class is coded as such. And yeah, I already did this, so y train equals 6. So now let's get to the core of the work. So from Tensor, this is when we actually want to make our sequential model. We go from TensorFlow.keras.models, import sequential. And from TensorFlow.keras.layers, import dense, maxpool 2D, conv 2D, and flatten. Okay. Now, building a sequential model, as I expect you already know, is model equals sequential. Then we go ahead and we add the desired layers. So as you know, there is no rule to this. Basically, you basically design these layers yourself, you experiment. But let's say we are going with this structure. So model.add conv2d, we are adding a convolutional layer with 32 filters and the kernel size of 4 by 4. We are defining the input shape, which resembles our images, 32, 32, 3. Remember, we don't put the batch size here. And activation is value, okay? Then we add a max pooling layer. Then we add a conv2d again. Then we do a max pooling. We then flatten the data, sorry, the output of the max pool. And we then feed this flattened layer, which is now one-dimensional vector, into a dense layer with 256 neurons, and we use a ReLU activation function. And finally, we feed the output of this into a dense model with 10 neurons, which is going to be our output technically because we have 10 classes, and we are using a softmax activation because we are using categorical cross entropy. As you're all aware, when we make a sequential model, we go ahead and we compile the model. Okay, so we compile it by defining our loss, by defining the optimizer, and by defining our metrics. Let's just say I'll just change this to Adam for the sake of it. Okay, so I'm going to click that, and now I have made my model. Okay, so if I say model.summary, it would basically give me the structure of the model that I just created. Okay, and that is it. After this point, you have made your model. Okay, so it's done. And from there on, you fit the model on the data. Okay, so you fit it on your training data, and you know, you wait for the certain number of epochs that you choose to complete, and you're done. You're done. Your model is fitted. Then you go by evaluating or like making predictions with it. Okay. So fair enough. Now, how are we going to do this in the functional API? So I'm going to go as usual. Okay. These are the steps that we just carried out. So no need to mention them. And so up to this point, everything was the same. Okay. Now I'm going to import some libraries, but this is where stuff starts to change. First, to focus on the gradient tape, I'm going to just go with the sequential model. Okay, so this is our sequential model. Now, when I'm talking about the gradient tape is where we would be undertaking the model.compile part of this manually ourselves, yeah? So first, forget about the functional aspect. We're just going to go with the sequential API, but we're going to be using gradient tape instead of using model.compile, okay? So everything so far is the same. Okay, I've put that in max pool 2D here. Yeah, that's everything is the same, okay? So up to this point, that part of the code is exactly the same as this. So I'm gonna go here, I'm gonna click basically run this. So I made a sequential layer model. But you notice now I don't have compile here, okay? Because I'm going to undertake the compile part myself manually. Now, let's ignore that bit, okay? Now here, let's look at it. Now, remember in the compile, we define the loss, we define the optimizer, and it's done, okay? But when we want to use the gradient tape, it's going to be different, okay? So first, I'm going to define a loss function, and the loss function is TensorFlow.keras.losses.categorical cross entropy, the same as that. So I could have had literally, instead of typing in categorical cross entropy, I could have put that here, okay? But remember, I'm not putting these as a parameter into any compile function, yeah? I'm just writing them separately. And I'm defining an optimizer. So technically, I could have named this Mickey Mouse and this as Jerry, okay? but these are the names that I choose to be relevant and basically to be up to the point. So I've defined my loss function and I've defined an optimizer. Now, from this point onward, it gets interesting. So I'm going to define a training step. Now I'm going to say define train step X and Y. Then I say with TensorFlow.gradient tape persistent equals true as tape. So I'm making an instance of TensorFlow.gradient tape and naming it a tape. Technically, it's like tape equals TensorFlow.gradient tape. With that, I'm making predictions equals model. Okay, so remember, I have already made my model. Just like the previous example, my model is the sequential model. So prediction equals model, and to this model, I'm feeding an x parameter, okay, which will be taken from here, the first parameter in the function, and I'm putting training equals true. Okay, so it means I want the model to be trainable. Then I'm defining a loss. What is this loss? So the first predictions would go and make predictions, okay? So the first the predictions are when the model goes and makes predictions, okay, by having an input X and being trainable. And then it would generate a loss. Where does that loss come from? By using the loss function and comparing the predictions with real Y values, okay? So far so good. We are making predictions and we are making losses. So this is a train step. It's just one step, yeah? So for one step, the model is fed some input data, it generates some losses, okay? And those losses are achieved by comparing the output of the model, getting one round of training with the training data, and then comparing those predictions with the true basically y values. And then the next step, gradients equals, so tape dot gradient. So this is a function that I'm calling from the gradient tape basically, because I have gradient tape as tape. So tape dot gradient, okay? And what do I feed to this function? The loss that I calculated just now, model.trainable variables. What are these trainable variables in a model? But these are the weights, okay? So gradients equals tape dot gradient. It takes the loss value and the trainable variables, okay? Then I'm doing something with my optimizer. So I'm using the function dot apply gradients with my optimizer. So optimizer dot apply gradients, and I'm zipping the gradients that I obtained, yeah, with model trainable variables, okay? And then I'm deleting this tape. Just something for you to understand with this persistent equals true. So when I'll put this here for you. So when you use TensorFlow.gradient tape to compute gradients, it records operations for automatic differentiation. So by default, a gradient tape is not persistent, which means that once you compute the gradient using this method, the tape is discarded and you cannot compute more gradients using the same tape, okay? So what is this persistence equals true? Now, like I always like to use analogies as much as I can. So imagine you have a piece of paper and we call this that tape, yeah, the gradient tape, yeah, which you're writing down some calculations. So without persistence, it's like you do your calculations, and once you're finished, you just get that piece of paper and you chuck it in the bin, okay? You throw it away. And then if you need to do more calculations, you just grab a new piece of paper. With persistence, it's like when you're carrying out your calculations, as you are finishing with one sheet of paper, you don't throw it away, but you keep it on your desk. But remember, obviously, you're using resources, like your desk space, for example, in this analogy. Um, that's what it means, basically. Okay, so you can read far more about it if you like, but that's what that means. Okay. And delta, it means that once you don't necessarily need to put this, but you would help with your resources, computing resources. So that's my train step. This is technically for one step, yeah, for just a single step of doing these calculations. All right. Now, what do I do next? Next, I'll define my batch size. Okay. So my batch size is going to be 32. Okay. Now I'm going to create a for loop. What is this for loop? For epochs in range 10. Okay. For epochs in range 10, it means I'm going to repeat something 10 times. Print f, this is f string print performing epoch number epochs. Okay. But then look at that. For I in range 0 to length of x train at batch size intervals. Okay, so for I in range 0 to that, yeah, the length of our x train. What's the length of our x train? Let's just code it out. Okay, so len x train. So from 0 uh, to from 0 to 50,000, basically, from 0 to 50,000 at intervals of 32, okay, perform this operation. Meaning what? We define an X batch. What is the X batch? From our X train, just doing a slicing, I to I plus batch size. So we're taking batches of 32 images from our X train. Yeah. So X batch at the moment is from 0 to 32. Okay. So 32 images. And Y batch is from our YCat train. YCat train, remember, was when we converted to categorical. We're taking the same number of batches. Okay. And then I'm calling my function train step. Okay. Train step. What was train step? We just made it here. That's my training step. So do you notice what's happening? So I've defined the train step, which calculates gradients and adjusts weights, okay, for just a single step. Then I'm using that function in a loop, which I'm running by selecting a 32 number of sort of samples, basically, i.e. a batch, and I'm running this operation. So I'm running the train step, okay? I'm running the train step for the number of samples in a batch. Okay, that's all I'm doing. What did trainer step do for us? It was adjusting these weights. Remember, our model training equals true, so things are getting adjusted in there. Okay, so let's do that. Sorry, what did I go wrong? Did something. Sorry about that. Was just a little typo, so nothing. So I just went through this. So I'm running this for loop, okay? And technically, what I'm doing here is, I want you to think. So up to model.compile, and then what do we do with sequential model? We do model.fit. So I'm going to run that simultaneously here as well. Okay. So technically, what we are doing here, okay, is that we are constructing the, let me just get rid of this. Okay, so we are basically doing this part manually. So the compile and the model.fit. The fit is basically, you can think of it as the part where we are running our for loop, because technically that's what's happening in there as well. So both models are basically being run. So I'm going to just pause the video and come back when this is done. Okay. Okay. So we are on the last level of epoch, basically with this, with the manual, way of fitting our model. And as you know, like I started this one a bit later, so it's taking time. But going back to this, so technically speaking, as I mentioned, up to a certain point, up to the point of making a model, yeah, making a sequential model, everything was the same, yeah. So everything was the same. It's this part that we just carried out manually, okay? It's this part. Now, from that point onward, once your model is trained, we're going to be making things the same way. So prediction equals model.predict. So we have our model.predict. It makes a prediction and exchange shape should be the same as prediction shape. So if I just put prediction dot shape, okay. Oh, sorry, X test. Okay, same thing basically. But remember one thing. Our predictions are going to be like, recall, they have 10 rows, yeah? So if I say predictions on the first one, you remember we have 10 columns, okay? And we are predicting by the highest probability basically as into which one this is. So in this case, I think it's 0, 1, 2, 3, okay? Class, that's 3. We need to convert this back. Do you remember our y test? So if I say or y test, okay, they were numbers, weren't they? Okay, so we want to convert these predictions. We want to convert these back into that, numerical sort of digit format. Okay, so I'm going to say batch predicted class equals np.argmax. The prediction axis equals 1. So using the argmax, okay, function. And if I now go and say, yeah, 3. So it basically just goes and finds the argmax, okay? The argument number, the maximum obviously is that. So 0, 1, 2, 3. And it just output that. So it's similar to our Y test, basically, not the Y cat test that we created for model training. Okay, batch break the class dot shape, we already did that. Y test shape, we already did that. Now let's just do some metrics from scikit-learn.metrics, import classification report and accuracy score. We are doing a classification, so accuracy score or Y test and our Y batch predicted class. So we have in a model 0.62 accuracy. Obviously, you have just run it for 10 epochs. And print classification report, and we are getting that classification report out. Okay. So at the moment, this model is still running, but obviously, we would just follow the same thing. Now, the sequential part. Okay. So far, what we did, yeah. I told you that everything we do is the same. So it was this model sequential and then model.compile. What if we wanted to write these in the functional format? Yeah. So instead of using a sequential API, what if we were to use the functional API? Well, very simple. So I'm going to have this here. Okay. So from TensorFlow.keras import layers and then model, and we define our input layer. So input layer equals layers dot input, capital I, remember. Shape, we give the shape. Then we make our conv1 layer. Or could have named this anything. Some people would name this as X and then like continue using XXX, but I think this is more clear. So conv1 layers.conv2d, filters, kernel size, activation number, and I'm feeding the input layer into this. Now, then I'm adding my max pool 1D, just like here, except that I'm feeding the conv1 into it. Then I'm making my conv2, just like here, and I'm feeding it with my max pool 1D. So, and so on and so forth. Then I'm having my flatten layer, and I'm having this as the output for the flatten. Then I get a single vector out, which I'm feeding to a dense layer of neurons, 256 neurons, just like that. Yeah. And then my output layer, okay, the same. Activation softmax, and I'm feeding it with dense one. So that is being fed into this. And finally, my func model, okay, my func model, I'm capping it basically, is models.model input layer, which was that, and output layer, which was that. Okay, and my model is made. So this, technically, everything you saw here is the functional format of this sequential format. Okay, so that and that are basically the same thing. This is the sequential format, that's the functional format. And from this point onward, if you're using gradient tape, everything is the same. So here, for example, I put model equals model because I've named my sequential model as model, and I named my functional model as func model. So I'm just going to put func model. Okay, so func model, and then everything is the same from this point onward. So if I click this, and if I do that, everything is performing the same way. Okay, why? You might be like, where did this model come from? Remember, this is where I'm using the model. Okay, because I named the model as func model now, so it's using the functional API built CNN model. Okay, and just to sort of as a fun bit of work, like this was our sequential model. Let's see how does this perform. But technically, they should be the same. Okay, so again, predictions. These are all the steps that we already carried out here on the other window. So I'm not going to just bother explaining. Batch predicted classes and accuracy score 0.685 and print classification report and 6.9. What do we get here with this model? Previously when we run it, we had 6.2. This has nothing. This has nothing to do with the fact that we use the sequential or we use the functional or we use the gradient tape or we use the compile. Okay, so I want you to be aware of that. It has nothing to do with it. It just, basically, like by chance, the random bits that were selected, even like this. So this is a very small number of epochs for such images anyway. Well, I hope you have enjoyed this. So perhaps one last sort of recap I thought may be good if we go back again when it comes to the compile. So remember, with the gradient tape, the gradient tape section is covering this bit. Okay, so what do? We define the loss function, we define our optimizer, then we define the training step. Although, sorry, we don't define it here, we just set it, yeah? So defining, I mean, like, really I should use it for making the function. So we allocate our loss function, we select our optimizer, then we define a training step. And then we say with TensorFlow that gradient tape, persistence equals true as tape, predictions equals our model, whatever model we have made, x, training equals true, loss equals loss function, y predictions. Okay, the predictions comes from here. Y is going to be already set. Gradients equals tape.gradient method. Yeah, and to that we give the loss and the model.trainable variables. Okay, and optimizer dot apply gradients is a method that we call of the optimizer. And we zip in the gradients and the model trainable variables. Okay, and that is it. Then with this method that we created here, we feed this method in our for loop, which is technically the model.fit. Okay, so when we do this, this is like we are running the fit. Okay, we define the number of epochs ourselves, but this is really the range of epochs. I could have put here epochs equals whatever number and then use that variable that name that I choose to put it here, but I thought like this is simpler. And then this is obviously just to let me know where we are with the training. And then we create a for loop for I in range 0 to the length of our data, training data, at intervals of batch size. Okay, we are going to be selecting our X batches or Y batches. Okay, and then be calling the function that we created. So for that many number of epochs, we go and basically, adjust the weights in our model, and then our model is basically trained as such. Okay, well, I hope you have enjoyed this, and definitely, I think if you like, you can go ahead and copy this code, and code along with this video, and it should give you a better perspective. So this was sequential API versus functional API with using gradient tape. Thank you.